In this video, we're going to look at section, whoops, let's not use the highlighter, section 14.1, which is iterated integrals. So we've talked a lot about differentiation and how that looks with multivariable functions. And so the natural next step is to look at integration. I'm going to go ahead and switch to black. Okay, so suppose that we know partial derivatives, say fx of xy is 4y squared x. Well, could we figure out what f was? What if we tried integrating? So consider the integral of 4y squared x with respect to x. Well, that should be f of xy. Now, when we integrate with respect to x here, so dx is telling me I'm integrating with respect to x, I'm going to treat y like a constant, just like when we differentiated with respect to x, we treated y as a constant. So treat y like a constant. Okay, so if I do that, I just have a function that's linear in x. And so my rules for integration say that I'm going to take that power up by 1 and then divide by that. Now this is an indefinite integral, so I need plus c. But here c could be a function of y. So we're going to write this as c of y, where c is a function of y, which may include a constant term. And that cleans up a little bit, so I get 2y squared x squared plus c of y. Now what if I put some bounds on the integral? So what if I integrate from 0 to 3y, 4y squared x dx? Well, when we have definite integral, we're just going to integrate with respect to x, like we did above, but we don't write down the plus c here. So from 0 to 3y, and it might help you to think about these were bounds on x, right? So x equals 0 to x equals 3y. And we just plug in like we would normally. So I get 2y squared times 3y quantity squared minus 2y squared times 0 squared. And that's going to give me 4, nope, not 4 at all, sorry. Let's see, I have 2 times 9, that's 18, and then y squared and y squared, so y to the 4th, 18y to the 4th. Okay, so I want to make a comment here. We can't have the variable of integration also in our bounds of the integral. Okay, so I couldn't have a function of x, for example, as my lower or upper bound in this integral if I'm integrating with respect to x. And in general, we can integrate from a function of y, h1 of y, to h2 of y, f sub x, xy, with respect to x, so dx. In general, that's going to be f of xy evaluated from h1 of y to h2 of y. And so I'm going to plug those h functions in for x, so I get f of h2 of y, comma y, minus f of h1 of y, comma y. Whoops. I'm just going to write similarly for integrating fy of xy. So here, if you were integrating fy of xy, you would have bounds that are functions of x here, and you would have a dy because you're integrating with respect to y. Okay, I'd like you to try a problem. Try integrating from 0 to x, the function x plus 5y with respect to y. Now, I've put a sample problem for you to try in WebAssign, and so what I'd like you to do is try that problem and then get your answer and then come back and watch the next part of the video.